Hello. Hello.
जी सर.
Can you hear me?
Yes sir.
All right. Okay, we start this online session of functional analysis. This is 7th week of the course, and today is the 26th December 2020. If you remember in our previous lecture, we defined name of an operator. Name of an operator is defined by three formulas, and we said that these three formulas are equivalent, but we didn't prove the equivalency because the proof was too lengthy. Today, inshallah, we shall define isomorphism, isometric isomorphism, and topological isomorphism. Okay, tell me, can you see this slide?
Yes sir.
Right. Okay, we start with the definition. You see, isomorphism is an operator from one nonlinear space into another nonlinear space satisfying two conditions. Those two conditions are that the operator must be linear and one-to-one. Now here are three conditions are written. Condition A, which says that the image of x plus y under this operator t is equal to image of x under t plus image of y under t. And B condition says that image of alpha x, where alpha is a scalar, it is equal to alpha image of y under this t. Together, these two conditions are the conditions are of linearity. Or in other words, you can say that your operator t is linear. And the second condition, or condition C, which says that t is one-to-one. And you know that when an operator is t is one-to-one, an operator t is one-to-one, if every element in the domain space has a distinct image in the range space under this operator. So if these two conditions are satisfied by an operator from one nonlinear space into another nonlinear space, then this T is called isomorphism. And the two nonlinear spaces, x and y, are said to be isomorphic if there exists an isomorphism from x onto y. So note this condition onto. The two nonlinear spaces x and y are said to be isomorphic if there exists an isomorphism in the above sense from x onto y. And we say that an operator or function is onto if its range is the whole space y, or tx is equal to y. If f is a function, then fx is equal to the whole range space, set or space y. Similarly, if we put one additional condition on the isomorphism, then this isomorphism is called isometric isomorphism. And the condition is that Tx now is equal to x now for all x in the domain space X. If this additional condition is satisfied by the isomorphism T, then T is said to be isometric isomorphism. Isomorphism and isometric isomorphism. An isomorphism is said to be isometric isomorphism if this additional condition, that is Tx nam is equal to x nam for all x in X. And as before, the spaces X and Y are said to be isometrically isomorphic if there exists an isometric isomorphism from the nonlinear space X onto, please note this onto condition, from X onto Y. And there is another definition which is called topological isomorphism. We started with the definition of isomorphism. An operator T is said to be isomorphism. It is linear and one-to-one. And this isomorphism is said to be isometric isomorphism if these conditions of Tx nam equal to x nam for all x is satisfied. And the isomorphism is said to be topological isomorphism if T and T inverse are continuous. T is an isomorphism from X into Y, and if T inverse exists, this T, that is the linear isomorphism, T is linear and its inverse, T inverse from Y to X is continuous, then this isomorphism is said to be topological isomorphism. Let me repeat once again. An isomorphism T from a nonlinear space X into a nonlinear space Y is said to be a topological isomorphism when if T and T inverse are continuous in their respective domain. Respective domain means if T is an operator from domain X into range Y, then T inverse will be an operator from Y into its range X. This is what we mean by respective domain. And the spaces X and Y are said to be topologically isomorphic if there is a topological isomorphism from X onto Y, or you can say that if there is a homeomorphism T of X onto Y, this topologically isomorphic can also be stated as if there is a homeomorphism T of X onto Y, that is also a linear operator. For this reason, X and Y may be called linearly homeomorphic. Sometimes, instead of saying that X and Y are topologically isomorphic, we say that they are linearly homeomorphic. And what is the reason for saying this? The reason is that if you recall your memory in topology, we say that a map T from a topological space into another topological space Y is a homeomorphism if it satisfies three conditions. The first one is that the map T is continuous. Second, this map T is one-to-one and onto or bijective. And third, T inverse is continuous. If these three conditions are satisfied by the map from topological space X into another topological space Y, then this map is called homeomorphism. Here you see that when we say that T is a topological isomorphism from a nonlinear space X into a nonlinear space Y. That means that T and T inverse are continuous. And the onto the 1-1 condition is satisfied by isomorphism, and the onto condition is given that from X onto Y. So the three conditions of homeomorphism also satisfied by this topological isomorphism. So in other words, it is a homeomorphism, because you know that every non-linear space is a metric space. We have proved this result. And you also know that a, a metric space is a topological space. So in this way, a non-linear space is a topological space. So here this X and Y may also be considered as a topological space. So you may use the term homeomorphism instead of this topological isomorphism. So these are three definitions which we shall use in our later work. Homeomorphism, isometric isomorphism, and topological isomorphism. The spaces are said to be isometric if there exists an isomorphism from X onto Y, and the spaces are said to be isometrically isomorphic or congruent. Remember this word congruent as well. For isometric two spaces said to be isometrically isomorphic, and instead of isometrically isomorphic, we can say that they are said to be congruent. So this is alternate word for the topological isomorphic. Hello. Right, we move to the remark. The remark says, in order that X and Y are congruent, or as I said, isometrically isomorphic. So you may use these two terms, isometric isomorphism and congruent, interchangeably. So X and Y are said to be congruent if it is the necessary and sufficient condition is that there exists a linear operator T with domain X and range Y such that T inverse exists and Tx norm is equal to X norm for every X in X. This is the necessary and sufficient condition for two spaces to be congruent. Second remark says that two nonlinear spaces may be topologically isomorphic or linearly homeomorphic. As I said, you may use these two terms interchangeably, but not necessarily congruent. There exist examples which show that two nonlinear spaces may be topologically isomorphic, but not necessarily congruent. Third remark, remember that topological isomorphism is an equivalence relation. Hello, please. Hello. हेलो बच्चों को खामोश कर लें, दूसरों को डिस्टर्ब कर रहे हैं आप. Can you hear me? Hello.
Yes, sir.
Now, what does the equivalence relation mean? We said topological isomorphism is an equivalent relation. This means that if it is reflexive, second symmetric, and third transitive. If these three conditions are satisfied by this topological isomorphism, then we say that it is an equivalence relation. We recall one result from journal topology. It says that it's the definition of in fact a topological property. When a certain topological space satisfies topological property, by topological property we mean that a property possessed by a topological space is also possessed by all topological spaces homeomorphic to that space. This means that if X is any topological space and there are other topological spaces which are homeomorphic to this topological space X, now the properties possessed by X are also then possessed by the other topological spaces. This is called topological property. Let me repeat once again. If X is a topological space and it has certain properties, if there are other topological spaces which are homeomorphic to X, then the properties of X will be possessed by all other topological spaces which are homeomorphic to X, and vice versa. Means the property possessed by the other topological spaces will also be possessed by X. So these are some remarks on definitions, and in the last remark we recall the definition of topological property, and these remarks we shall use in our later work. Now we prove one result about topological isomorphism. You know that by definition, if X and Y are two nonlinear spaces, then they are topologically isomorphic if there exists a topological isomorphism from X onto Y. This is by definition when two nonlinear spaces are topologically isomorphic. Now we prove a result. Instead of checking the conditions of the definition, we prove one simple result. And that result says that if X and Y are two nonlinear spaces, then these two nonlinear spaces are topologically isomorphic. कब होंगे topologically isomorphic? If and only if there exists a linear operator T with domain X and range Y and two positive constants small n and capital M such that this inequality is satisfied. That is, M times X now is less than equal to T X now less than equal to capital M X now for every X in the domain space X. If this inequality is satisfied, then the two nonlinear spaces will be topologically isomorphic or linearly homeomorphic. अब अगर पेपर में टोपोलॉजिकली आइसोमॉर्फिक की जगह linearly homeomorphic आ जाए, it doesn't make any difference because these two terms are equivalent. Proof is simple. पहले हमने शो का assume करना है that there exists a linear operator T with domain X and range Y and two positive constants small m, capital M, satisfying the inequality M times X now less than equal to Tx norm less than equal to m x norm for every x in x.
Sir,
और फिर प्रूव क्या करना है? We have to prove that x and y are topologically isomorphic or linearly homeomorphic.
सर आप पेज 20 पे हैं या 21 पे?
By 20, sorry, let me change this side. This is 21, right?
Okay, sir.
Thank you very much.
You're welcome, sir.
And this theorem is on page 21. So look at this statement once again. If x and y are nonlinear spaces, they are topologically isomorphic if and only if there exists a linear operator T with domain x and range y and two positive constants, small m, capital M, such that m times x norm is equal to, less than equal to, Tx norm less than equal to capital M x norm for every x in x. So we assume that there exists a linear operator T and two positive constants small m, capital M satisfying this inequality, and we have to prove that x and y are topologically isomorphic. कब topologically isomorphic होंगे? When there is a topological isomorphism from x into y onto y such that, and topological isomorphism क्या होता है? When T and T inverse are continuous. So we assume that this inequality is satisfied, and we have to prove that x and y are topologically isomorphic. Now you see, we may split this inequality into two inequalities. वो कैसे? First consider m times x now less than tx now. ये एक inequality बन गई. And then consider Tx now is less than equal to mx now, which is another inequality. So you may split this inequality into two as follows. If you remember, we proved one result which says that if T is a linear operator from a nonlinear space X into another nonlinear space Y, then T inverse exists and is continuous if and only if m times x norm is less than equal to Tx norm for all x in X. We have proved this result in our previous lecture. Now you see this inequality, m times x norm is less than equal to Tx norm is your first inequality, equality number 2, right? And when this inequality is true, then T inverse exists and is continuous, right? This is by previous result. We are not doing anything. We already know this. If this inequality is true, then T inverse exists and is continuous. This is one result. We have already proved. And if you remember, we have already proved another result which says that if T is continuous, then it is bounded. That is satisfying the second inequality. Bounded का क्या मतलब? If there exists a constant m greater than 0 such that Tx norm is less than equal to m x norm. And this inequality is also here, right? We have this inequality. When this inequality is true, then T is bounded or continuous. No, we have two results. The first one says that T inverse is T inverse exists and is continuous if and only if m x norm is less than equal to Tx norm. And the second result says T is continuous if and only if Tx now is less than equal to Mx now. Now there is if and only if in both results. Now what you have on the left hand side, in the first result you have on the left hand side T inverse exists and is continuous. And in the second result you have T is continuous. And on the right hand side of the first result is inequality m small mx now is less than equal to Tx now. And in the second result, you have Tx now less than equal to capital Mx now. Now combining these two results, on the right hand side, you will get T inverse exists and both T and T inverse are continuous. If and only if, then on the right hand side, you have these two inequalities. If these two inequalities are satisfied, altogether, you can write this in one inequality, mx now less than equal to tx now less than equal to capital M x now. Now, this statement is equivalent to saying that the right hand side is T inverse exists and both T and T inverse are continuous. ये किस चीज की डेफिनेशन आ गई? दिस इज द डेफिनेशन ऑफ the two nonlinear spaces x and y are topologically isomorphic. So instead of saying that T inverse exists and both T and T inverse are continuous, you can say that x and y are topologically isomorphic if and only if m times x nam is less than equal to Tx nam less than equal to capital M x now for all x in x. And this completes the proof of this simple result. Let me repeat once again. आपके पास definition है topological isomorphism की, और those spaces by definition when they are topologically isomorphic, if T and T inverse exist and are continuous. Now instead of using this result, this definition, we prove this simple result which gives you a criterion when two nonlinear spaces will be topologically isomorphic. The criterion is that if there exists an operator T with domain X and range Y and two positive constants small m, capital M, such that this inequality m times x now less than equal to Tx now less than equal to capital M x now for every x in X. And this is one result about this topological isomorphism. Any question about this result? Hello, boys. Any question?
No, sir.
No?
No, sir.
Okay.
Not.
Right. Next is one definition. Listen carefully. If you remember, we may define more than one norm on the same linear space. When we were constructing nonlinear spaces, in some cases we defined more than one norm on the same linear space, as was the case of Rn or Cn. Rn, n-dimensional Euclidean space, and Cn, n-dimensional unitary spaces पे हमने दो नाम डिफाइन किए हुए थे. Now, if X is any linear space and two norms are defined on this linear space X, when these two norms will be equivalent, By definition, if norm 1 and norm 2 are two norms on the same linear space X, then norm 1 is equivalent to norm 2 if and only if there exist two positive constants small m and capital M such that small m x norm 1, दो नाम हमने डिफाइन किए हुए, multiplying norm 1 with small m, if this is less than equal to norm 2, and then norm 2 is less than equal to capital M norm 1. Small m, capital M are two positive constant. If we take norm 1 on the two extreme and norm 2 in the middle, and we satisfied M1, norm 1 with small m and the same norm 1 with capital M, and put the norm 2 in the middle, if this inequality is satisfied for all x in X, then we say that the two norm 1 and norm 2 are equivalent. और अगर आप norm 2 को पैरेलल रखना चाहते हैं, then the definition will be norm x norm 2 less than equal to x norm 1 less than equal to capital M x norm 2. आपकी मर्जी, इस तरह लिखे या उस तरह. In both cases, these two norms will be equivalent. So let me repeat once again. X is in a linear space and two norms, norm 1 and norm 2 are defined on X. These two norms by definition will be equivalent if and only if there exist two positive constants small m, capital M such that m x norm 1 is less than equal to x norm 2 less than equal to capital M x norm 1. If this inequality is satisfied, then we say that the two norms are equivalent. जैसे पिछले केस में, पिछले theorem में, when two norm linear spaces will be topologically isomorphic, एक तो हमारे पास definition है, if there exists a topological isomorphism from X onto Y. यहाँ पे हमारे पास equivalent नाम की definition आ गई. When two norms are equivalent, if and only if that inequality is satisfied. No, we prove is the one result, and this gives us a simple criterion when two norms on the same linear space will be equivalent. The result says, let X be a linear space and suppose two norms, X norm 1 and X norm 2 are defined on X. Then these two norms define the same topology on X. When these two norms will define the same topology on X, if and only if there exists two constants small m, capital M, such that m x norm 1 is less than equal to x norm 2 less than equal to capital M x norm 1 for all x, or in other words, norm 1 and norm 2 are equivalent. एक condition लिखे, या simply you can say that the two norms will be equivalent. इस स्टेटमेंट को आप इस तरह भी लिख सकते हैं, x and y are two norms. X is a norm linear space and two norms are defined on this linear space, norm 1 and norm 2. these two norms will be equivalent if and only if they define the same topology on X. This is the alternative statement. Proof is not difficult. X is a linear space and two norms, norm 1 and norm 2, are defined on this linear space X. No, X with norm 1 is denoted by x1, and the same linear space X with norm 2 is defined by x2. So in this way, you get two non-linear spaces. अगरचे linear space आपका वही है, लेकिन norm 1 के साथ it becomes a non-linear space. With norm 2, it is also a non-linear space. So you have two non-linear spaces, X with norm 1 and X with norm 2. X with norm 1 is denoted by capital X1, and X with norm 2 is denoted by capital X2. So there are two nonlinear spaces. Let X1 and X2 be the two nonlinear spaces that becomes with the norm 1 and norm 2 respectively. Right? अब आपके पास दो nonlinear spaces आ गए. Assume that T be a linear operator from X nonlinear space X1 into a nonlinear space Y such that Tx is equal to X. T आपका linear operator है और उसको आपने इस तरह define कर लिया that Tx is equal to X. अब हमने प्रूव क्या करना है? ये तो हमने दो non-linear spaces construct कर लिए, and we define the operator between them, that is T from X1 into X2 by Tx equal to X. अब हमने प्रूव ये करना है that first we assume that norm 1 and norm 2 are topologically norm 1 and norm 2 are equivalent, and we have to prove that they define the same topology, and vice versa. We assume that norm 1 and norm 2 define the same topology, and then there exist two positive constants, small m, capital M, satisfying that inequality. So first assume that there exists constants small m, capital M, both positive, such that mx norm 1 is less than equal to mx norm 2 for all x in X. Or in simple word, assume that m1 and m2 are equivalent. ये आपकी assumption हो गई या supposition. Since Tx is equal to X, या ऑपरेटर आपने डिफाइन किया हुआ है ऊपर. So replacing this X by Tx, because Tx is equal to X, so the above inequality becomes m x norm 1 is less than equal to Tx norm 2. ये norm 2 में जो x है इसको हमने रिप्लेस किया by Tx, which is less than equal to m times x norm 1 for all x in X. अब previous result में हमने प्रूव किया that m norm 1 is less than equal to Tx norm 2 less than equal to m x norm 1 for all x in X, if and only if x1 and x2 are topologically isomorphic. By previous result, ये पिछले रिजल्ट में हमने ये रिजल्ट ये प्रूव किया हुआ है. Now using that, you can say that mx norm 1 is less than equal to tx norm 2 less than equal to capital M x norm 1 for all x in x. If this inequality is satisfied, then we say that x1 and x2 are topologically isomorphic. और x1 and x2 कब topologically isomorphic होंगे? By definition, if and only if T inverse exists and T inverse are both continuous. अब ये स्टेटमेंट किसके बराबर है? When we say that T is continuous, this means that आप टोपोलॉजी जरा ज़हन में ले आए. टोपोलॉजी में हमने एक रिजल्ट प्रूव किया हुआ है. इफ टी इज a map from topological space X into a topological space Y, when this T will be continuous. एक तो आपके पास डेफिनेशन है कंटिन्यूटी की, when a map from one operator topological space into another topological space is continuous. और एक नहीं बल्कि दो रिजल्ट भी है हमारे पास which are used as definition of continuity of the operator. First result says if T is a map from a topological space X into a topological space Y, then this T is continuous if and only if the inverse image of any open set, say U in the range space, is open in X. यह रिजल्ट है हमारे पास. U में कोई Y रेंज स्पेस में कोई ओपन सेट ले और T के इनवर्स इमेज के अंडर जाहिर है that will be T inverse U will belong to X. If T inverse U is open in X, then we say that T is continuous. The second result says if T is in a map from topological space X into a topological space Y, then this T is continuous if the inverse image of any closed set in Y is under this map, the inverse image of U under this T is open in X. ओपन सेट ले रेंज स्पेस में और T के इनवर्स इमेज के अंडर ये ओपन हो इन X, देन वी सेड T इज कंटिन्यूस. या कोई क्लोज सेट ले इन द रेंज स्पेस Y और T इनवर्स के अंडर अगर ये ओपन है इन X, सॉरी क्लोज्ड इन X, देन वी से दैट इट इज कंटिन्यूस. ये दो रिजल्ट हमारे पास है. अब ये यहाँ पे देखें, we say that T and T inverse are both continuous. Up first using this result, when T will be continuous if the inverse image of any open set. Open sets क्या होते हैं topological space में? Elements of the topology, right? जितने भी ओपन सेट्स है उनका इमेज अगर X में अंडर T इनवर्स ओपन हो, देन ओपन का X में कब ओपन होंगे? अगर वो T टोपोलॉजी को बिलोंग करेंगे, X की टोपोलॉजी को. सिमिलरली T इनवर्स इज कंटिन्यूस. T इनवर्स क्या होगा? फ्रॉम Y टू X. अब X में कोई ओपन सेट लें और T इनवर्स के अंडर अगर वो इनवर्स के अंडर अगर Y में ओपन हो, then this T inverse will be continuous. अब यहाँ पे given है both T and T inverse are continuous. So this means that जो X से टोपोलॉजिकल सारे ओपन सेट से वो Y में ओपन है और जो Y के ओपन सेट से वो X में ओपन है. This means that X and Y have the same topology. इसका मतलब ये when we say the result says that X is a linear space, two norms are defined on this linear space, and this two norm linear space define the same topology on X if and only if the inequality is true. Define the same topology on X means that the open sets of x1 are open in x2. यहाँ पे आपके open spaces x1 और x2 है instead of x and y. x1 के जो एलिमेंट ओपन सेट से वो x2 के ओपन सेट से और x2 के जो ओपन सेट से वो x1 के ओपन सेट से. So this result says that ये फिर से आ जाए hence by theorem this inequality is true if and only if they define the same topology, right? And this completes the proof. और ये आज के लिए काफी है क्योंकि सारी थ्योरी थे. अब अगर कोई क्वेश्चन है आज के लेक्चर पे, यू आर मोस्ट वेलकम. हेलो. हाँ जी.
नहीं है सर कोई क्वेश्चन.
हाँ,
थैंक यू.
कोई नहीं. ये जरा पढ़ ले. एक्सप्लेन तो मैंने कर दिया सब कुछ, लेकिन अब वो जो क्लास
जी सर
में जो सिचुएशन होती है वो तो नहीं बन सकती यहाँ पे. बहरहाल नोट्स बिल्कुल क्लियर है.
जी जी जी.
मैंने जो जहाँ पे कोई कमी थी साइट पे वो भी मेंशन किया हुआ है. इंशाल्लाह कोई मसला नहीं होगा. एक दो दफ़ा पढ़ने तो समझ आ जाएगी. अच्छा, दूसरी बात,
जी सर,
आपने अगर यूनिवर्सिटी का पोर्टल देखा होगा, मैंने पहला असाइनमेंट अपलोड किया हुआ है फंक्शन एनालिसिस का भी और एडवांस कैलकुलस का भी. असाइनमेंट 1 20 मार्क्स का असाइनमेंट है. पोर्टल देख लेना. 10 जनवरी लास्ट डेट है फॉर सबमिशन ऑफ द असाइनमेंट. पोर्टल देखा है आपने? असाइनमेंट किसी ने देखे?
जी 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 देखा है सर. देखा
अच्छा
है
अच्छा
सर.
अच्छा. बस मैंने रिमाइंड कराना था, मैंने कहा आपको बता दूं. हो सकता है किसी ने ओपन ना किया हो ना. बाकी दोस्तों को भी बता दे कि
जी सर,
असाइनमेंट ऑलरेडी अपलोड हो चुका है.
सर ये असाइनमेंट हैंड रिटन नहीं होगा?
हाँ,
असाइनमेंट हैंड रिटन नहीं होगा?
नहीं, ये आपने आप हैंड रिटन भी कर सकते हैं. आप हो सकता है कोई टाइप ना कर सके तो साफ लिख लें और फिर उसको अपलोड कर लें. ठीक है, उसी पोर्टल पे. वो फिर हमें मिल जाते हैं ना. जैसे मैंने अपलोड किया हुआ इसी तरह आप भी अपलोड कर लें. स्टूडेंट अपलोड करते हैं असाइनमेंट, बेशक हैंड रिटन हो, कोई मसला नहीं, लेकिन डिटेल आपने सारी लिखनी है. सिर्फ आपको चेक करना है कि आप कैसे मतलब असाइनमेंट को सॉल्व करेंगे. अब न्यूमेरिकल क्वेश्चन तो है नहीं फंक्शनल एनालिसिस के असाइनमेंट में. आपने स्टेप्स सारे लिखने हैं कि आपने करना क्या है, कैसे इसको प्रूव करना है. असाइनमेंट इजी है. आपके पास कोई ऑपरेटर है फ्रॉम लीनियर स्पेस एक्स इनटू अनदर लीनियर स्पेस वाई, और आपने प्रूव करना है दैट द कर्नल ऑफ टी, इसको नल स्पेस भी कहते हैं, दैट इज क्लोज्ड लीनियर सबस्पेस. लीनियर सबस्पेस शो करना है कर्नल ऑफ टी को और क्लोज्ड. ये है आपका फंक्शन एनालिसिस का असाइनमेंट. और एडवांस कैलकुलस में उसमें भी एक क्वेश्चन है. आपके पास कंटिन्यूस फंक्शन है और उसके आपने मिक्स पार्शियल डेरिवेटिव फाइंड आउट करने. ऑलरेडी लास्ट वीक भी हमने क्वेश्चन किए थे काफी इस पे. यूजिंग दोस टेक्निक्स you can find the mixed partial derivative, that is f of xy and f of yx. ये दो मिक्स पार्शियल डेरिवेटिव आपने फाइंड आउट करने. बस یہ لیکچر تو ختم ہو گیا انشاءاللہ. We shall start the other lecture very soon. Don't go away please. آپ نے جانا نہیں, میں اس کو کال کرتا ہوں, وہ آ جائے بندہ دوسرا اپلوڈ کر لے,
ٹھیک ہے سر.
کیونکہ میں نے کہیں پہ جانا ہے. ٹھیک ہے, آپ جائیں مت, 11
ٹھیک ہے
بجے تک ویٹ نہ کریں نا, اس کے بعد اسٹارٹ کرتے ہیں. میں اس کو بلاتا ہوں تاکہ وہ اپلوڈ کر لیں ایڈوانس کیلکولس کا لیکچر بھی. ٹھیک ہے,
ٹھیک ہے سر.
اوکے اوکے, سی یو ان اے مومنٹ.